I feel honored to be the first talk this week, as it usually goes. I talk about all the things that are wrong with the platform, and then I sit the rest of the conference and listen to everybody tell me how they're going to fix it. So that's good. This talk, in my classic form, did not exist about 12 hours ago. About 8:30 last night, as usually happens, I looked at my outline and thought, okay, I don't have enough content. At about 12:30, when I was trying to finish it up, I realized that I had way too much. So I trimmed this down, but we're going to get right into it now. So it's the hard parts in the schedule. Really, the main thing here is how we're subverting the JVM. We're using the parts that work for us and routing around or avoiding the parts that don't. And I'm going to talk about the ones I could fit in here. This obviously isn't going to be a comprehensive list, but there's a lot of problems, a lot of things we've had to work around. But hopefully these will be the key ones for this room and the interesting ones for folks that work on OpenJDK. I have spoken here every year except the year I missed. I work at Red Hat in the Polyglot group. We've got a bunch of folks working on various JVM languages, working on JVM language extensions to JBoss and other Red Hat Java-based projects. I think that's about all that's interesting there. So, again, very happy to be the first one. This is my favorite event of the year because I don't feel like I'm talking over every single person in the room, talking about JITs and FFI and everything else at any other conference, Java, Ruby, or otherwise. Usually I think I'm losing everybody, but I know that at least a few people here are going to be able to keep up with everything. I'm going to go quickly through this. So if I talk too fast, let me know. If you want to ask a question, you can wait till the end or grab me a beer and I'll go into depth on any of these subjects, which are wide-ranging. So most folks should know at least a little bit about Ruby. It's a dynamic language, object-oriented language, kind of modeled on Python, Perl, a little small-talky, Lispy stuff in there too. Created by Mott's. I think originally like the 0.1 or the first official release was 93 or so. So it's been around for quite a while. Didn't really get popular until about 2000, 2002 when the first books in English came out. And then of course Rails really kind of launched it into popularity, and then it's now up in Python range of number of users. Things to notice, the memes that we have typically in Ruby, rather than in Python where there's one way to do it, there's more than one way to do it in Ruby all the time. Minneswan, which is Mott's is nice, and so we are nice, which is kind of the attitude that Ruby is trying to take towards development and community and whatnot. Convention over configuration, lots of little bits and pieces that have come out of Ruby over time. And here is one little Ruby example, just so people who haven't seen the language can see what it looks like. Interesting things to note here, optional parentheses on calls, optional semicolons to end lines. Lots of things to make parsing really hard, and I'll talk about that very soon. JRuby then, of course, is Ruby for the JVM. We've been working on it for, well, it's been around since 2001. Tom Annabo and I have been working on it full-time since we joined Sun Microsystems in 2006. And we've managed to keep convincing companies to pay us to work on it all this time. Obviously, a lot of these other side projects come out of it, but we're doing pretty well. It's generally the fastest Ruby. We're still kind of waiting on some JVM level things to help us to beat the most optimized runtimes out there, but it's moving along. We put a lot of time into it. And what we've learned over these 7-8 years is that Ruby is really hard to implement, especially on top of the JVM where we don't have access to a lot of the low-level things we need. And so I'm going to take you through about 4 or 5 areas here where we have had complications and challenges of building Ruby. First of all, just getting it to run. So Parsing Ruby is a great adventure. Lots of people have started into the quagmire of trying to write a parser for Ruby using non-Yak, non-Bison parser generators, and they have almost universally failed to create a 100% correct parser unless they use something that's basically provides a Yak grammar and does the same sort of generation. It's not context-free, things that change along the way, and it's very large. The parser grammar is almost 12,000 lines of code in Ruby. To illustrate this a little bit more graphically, I thought I would show some slides of a few other languages grammars and how they are interrelated and how complicated they are. I'm not going to ask who knows what language this is. This is Python. Yes, this is Python. It's fairly simple, fairly straightforward. Not a lot of interconnection. There are a few areas that are a little bit weedy, but not too bad. Some of you might recognize this if you've ever done a map of the JavaScript grammar. Again, fairly well ordered, fairly down at the bottom gets a little crazy, but pretty easy to follow through this and understand what one parser construction is going to lead to, and so on. And then we have Ruby, which is a bit of a mess. This is, out of the languages that Nick Seeger analyzed in about 2006, 2007, when we were trying to update the parser, this is certainly the most complicated one that we were dealing with at the time. I imagine there are many that are much more complicated than this now. I stuck to dynamic languages because in general parsing is considerably simpler for dynamic languages. They don't have a lot of sigils and types and other stuff around. But, so this is what we have to deal with, and this is what we have to use. In our case, in order to build a Ruby parser, a long time ago they ported the Bison grammar to a tool called J, which is essentially a Yak for Java, also added some C++ support so you can use it for, or C#, so you can generate C# stuff. There's not a whole lot of projects in the world that use the J parser generator. I think in 2006 or so there was JRuby and Mono for their C# compiler. We're the only two that we knew of actually using this. And we do have a fork of this that we had to tweak because of some of the issues that we ran into. Now, of course, this is a gigantic parser, and it's generating a lot of code. And the array initialization, just for the productions of this parser, would exceed the amount of byte code you could have in a static initializer for the array we created. So we have to post-process it and break up that initialization into multiple blocks in the class we generate. It originally generates a giant switch with all of the production bodies right there. And as the language has gotten more and more complicated, that slowly first crossed the boundary for what Hotspot's willing to compile and JIT. We would get to the point where all of a sudden the parser just fell off a cliff and performance was 100 times slower. We have to take a look at the compilation logs. We can see that it's just dumping it because it's way too big. Again, this was 2006, 2007. The incremental compiler stuff might do better, but we're still hitting a large limit there. And then, of course, we can actually cross that 65K boundary if we're not careful. So, first thing we did was outline the case bodies, which pretty much universally in our code base now, if we have a large switch, we make sure that every case body is outside of that switch. Pretty much the only way you can get a big switch to optimize it all. We moved on from there to actually turning all of the callables into little, essentially, instruction objects, little command objects. And rather than having a big switch, we just do the next one, do the next one, do the next one. And then the parser actually ended up running faster with 400 and some tiny little inner classes as the case bodies, rather than using the switch at all, which is not saying a whole lot of good things about Hotspot's switch optimization. So there's one. Where's our optimizers? Who's working on Hotspot JVM optimization stuff? Come on, you got to let everybody in here know where you are, because they're going to have to talk to you. So this is a problem that we'd like to see improved. It's also, unfortunately, we've tried to be pretty much pure Ruby or pure Java as much as possible inside of JRuby, where we're not using Ruby or calling the native. And these classes take a long time to get going. JRuby's parser can be significantly faster than the generated C parser, but it takes 5 minutes or so of loading code. And unfortunately, by the time you're done, by the time you get through 5 minutes of the application, the parser's long gone. So we're not even concerned about the parser anymore. This is, again, an issue with startup and getting things moving. On the interpreter side, we've tried at least 4 different models of interpreters. The original one, when I came into the project in 2005, was just a visitor-based, which was reasonably easy to follow, but all that extra dispatch really kind of killed the interpreter performance, and it didn't provide opportunities to inline anything. Pretty much every call site there ended up being megamorphic, and so everything ran on its own, and then we had 3 or 4 frames between each node in the AST to execute. So that didn't work. A big switch was the next thing. Every node in the AST had an enum on it, and we used a big switch to decide what the next operation was. Basically moved the code out of the visitor into switch case bodies. That was pretty good, but then again we ran into the big switch issues eventually, because the interpreter is of a similar complexity to the parser. I did play with an experimental stackless-based interpretation of the AST, basically turning each of the ASTs into little function objects and then trying to maintain some state internally. It worked, and I could basically do, recursive depth of 1,000, 10,000, 100,000, depending on the memory available. It was incredibly slow, so we didn't continue on with that after the early experiments. The current version of JRuby 1.7 just does direct execution of the AST, essentially just walking down the tree, calling the next interpret method, and that has been the fastest interpreter that we've run into so far. Common productions that you see in the AST itself, in the structure of the language, end up inlining into each other, like argument processing ends up inlining into calls. It doesn't inline all the way through, obviously, which would be neat if we had an AST-based language framework that optimized for us. Maybe we'll hear about something like that later this week. But it worked pretty well, and it was good enough for interpretation. So now the new way, in JRuby 9000, which is the working title for the next big version of JRuby, and it has a lot of rewrites, so we thought we'd go with a really big number. This introduces a new IR that we're using to execute Ruby. It's pretty much a traditional style compiler, like a CS 101 kind of thing. Allows us to use some traditional compiler optimization techniques. We can do some constant propagation. We can do dead code elimination. We can do some type propagation, and we're getting into that stuff a little bit. The way we started this initially was to make sure that we could interpret this IR directly. We know that breaking Ruby down into its semantic pieces is going to be a lot more tiny operations than the AST would have been, so performance is going to suffer from that. But we're hoping that with the JIT stuff, we can take the IR, do all of these optimization passes before we generate bytecode, and then get the best possible performance out of it. Okay, so I believe JRuby is the only JVM language that is itself a mixed mode runtime. And a lot of working on JRuby has kind of been building a little VM on top of a big VM. We have both an interpreter and a JIT, and that was a conscious decision. At about JRuby 1.1 or so, 2007, 2008, we had to start deciding how we were going to do compilation, what we were going to do to move on from interpreter performance to get the full-on JVM performance. At that point, we could have said we're just going to generate bytecode, we're going to ditch this interpreter thing. It'll make things simpler, definitely make things simpler for us on the implementation side. But the early experiments showed that the cost of generating all that JVM bytecode was very high. Loading that bytecode, since we can't say, turn off all verification in the system, every method body having to compile immediately, every script that you run in Ruby has to run from top to bottom to define the class and define all the methods. It was just way too much code to load. And our startup time would have been even worse. It would have been massively worse than it is right now. The other thing that we discovered is that our interpreter actually runs faster than the JVM's interpreter. Probably because we're not doing as many small cuts to the execution of the code. But in general, we found that our interpreter, when JITted by the JVM, is faster than generating bytecode and having hotspot interpret it for some amount of time, both for startup and for whatever execution performance we get. So the interpreter gets hot very quickly, runs Ruby code faster than if we had 1,000 different pieces of class data that each had to individually JIT before they would run fast. So the interpreter was a practical measure to get startup faster, to give us a little time to decide what to compile and how to optimize it, and then to move on from there. I don't believe any other JVM language has gone as far with this as we have. Okay, so eventually we do need to get down to bytecode. The early JIT compiler, the one that we have in JRuby 1.7, basically just walked on the AST and translated it straight up. Fairly simple compiler translation. It did very minimal. Over time, we added a little bit more and more semantic analysis to see which kinds of calls it was making, what kind of frame data it needs that we can't stick on the JVM frame, certain patterns that we saw coming up in code a lot that we could optimize one at a time. But it was very cumbersome to try and do it this way. We were not really familiar with doing heavy tree transformations, to do optimization passes over the AST itself. The AST wasn't really structured for that. Each piece was too big to really do analysis of it and break it down. So again, we moved on to using the IR, and that's what we're going to be hitting in JRuby 9000. So with the IR, we can do a lot of these optimization passes all the way down to constant propagation, unboxing primitives, stuff like that. That was much more difficult to do in the AST, and much more heavyweight, even if we were to do tree transformations for that. So we get the advantage of being able to do those optimization passes easily. The per instruction bytecode for the IR is considerably simpler than what we had for the AST. In the AST, you had one node that was call, and all the logic involved in processing arguments, preparing closures, all that stuff was basically hidden in that box. Now we have separate options for prepare this argument. And it isn't even prepare this argument. It's evaluate this argument, stick it in a temp, evaluate this argument, stick it in a temp, create the block. Those are all separate instructions. The majority of JIT logic for the instructions is maybe 4 or 5 bytecodes that we have to emit for any individual IR. This is kind of boiling down to our JVM IR that's above bytecode level. Something we can then analyze, do some optimization passes over, and then emit the bytecode that will be the best possible we can do at that level. And so we have some early numbers here. So this is a simple, stupid numeric loop. Of course, Ruby is dynamic, so everything is an object, or it looks like an object at least. And so loops on the JVM, when we run them, we can't, in our old compiler, can't remove the boxing, can't remove the Ruby fixnum object that we wrap around it. So an implementation like Rubinius, which also has a JIT and has tagged pointers for all of its integral fixnum stuff, but twice as fast as this. Now, where this gets interesting, we've got some other implementations here. So we got JRuby 1.7 and Rubinius. Truffle, which some of you might have seen or heard about last year, starting to get more and more press for building languages. Truffle does a much better job of doing the unboxing and a lot of the other optimizations, mostly because Truffle's built on top of Graal, so they can emit the actual IR they need at the lower level to eliminate those allocations and to even bail out if they need to go back to an object. So that's pretty cool. Topaz is the PyPy-based Ruby, which seems to be dead. I have not seen any work done on that in quite a while. But anybody who's played with PyPy knows their big claim to fame is that they have incredible escape analysis. Unfortunately, they can't run multiple threads yet, so that kind of limits the capabilities that we can do with Topaz, but better than Truffle, at least when I did the measurements for this. And then playing with JRuby 9000 with our unboxing, where we speculatively turn what look like integer operations into just raw, long operations at the JVM level, about twice as fast as the PyPy-based Ruby for this simple benchmark of doing a loop. Now, for something a little bit more complicated than just a numeric loop, Mandelbrot, this is, of course, one where Truffle is still doing better. They're able to emit more code, better code for fallbacks. They don't have to constantly be checking if they've overflowed into an object range of an integer, stuff like that. We have limited capabilities that we can do at the JVM bytecode level to do this sort of specialization optimization. We're looking to the JavaScript guys to help us, the Nashorn guys to help us with that aspect of stuff. But we're still doing pretty well. Even on this one, it's 4 or 5 times faster than JRuby 9000, JRuby with Indy, fastest possible, most recent JVMs. We're still not getting at least the unboxing performance out of Indy, and there's a lot of other issues as well. So we kind of decided that we're tired of waiting for the JVM guys to just make JRuby magically faster. We're going to take the next step and do these optimizations before we make JVM bytecode. All right, so what about Truffle? Some of you might have seen Ruby Truffle mentioned last year. So the big news was that after much whining and gnashing of teeth on my part, for the most part, the Oracle Labs guys saw fit, and the Oracle Labs lawyers saw fit, to allow us to roll Ruby Truffle into JRuby's code base with our licenses and everything. So JRuby 9000, when it releases, will have Ruby Truffle built in. We don't know if it'll be compatible enough to say you can run your application either with Truffle runtime or with the IR runtime. But at the very least, we're thinking for specific methods that Truffle knows how to optimize, we might be able to say truffleize that math method optimize that one and make it work well, and then other ones we can let the existing runtime do. So this is still early stuff. Peak numbers are really good. Startup and steady state seem to have some issues, but it's still exciting, and we're glad to have Chris working on Ruby Truffle as part of JRuby now. So the last one in this section, the JVM tricks we have to do to get performance, get things to work well. I won't talk too much about the first one. I got some slides for that. We are manually splitting up methods just to beat the limits. Most folks that generate any or do any JVM language stuff for most folks that do any JVM language stuff will have to do this at some point. It's very cumbersome to do it. It should be easier with our IR because the IR is basically broken up into logical blocks. So if we wanted to emit a particular block or the rest of the CFG, once we've reached a certain limit, to a separate method and just go to there, we'll be able to break it up. It'll be completely transparent in the compiler. Exception handling was kind of a pain. You can do an inline rescue in Ruby. So print out this function call. If that function call fails with an exception, return some default value. So a rescue or an exception handling can be used as an expression, so we had to use some tricks to avoid losing all of the current state for the call that might be wrapped around it. And we spent lots of time playing with JIT flags to try and get things faster. What I've learned is that playing with the JVM JIT flags is just a path to sadness, because either it won't do anything and you won't get any performance improvement out of it, or it will do something, it'll make things much better, and you still can't use those flags because you can't tell users to go and set inlining limits up higher. So, you know, we feed this information back to the JVM guys. We need these flags to get it to run fast, but we can't use them. Do it right on your side. And then, of course, we're using unsafe for lots of stuff. Things like doing a 64-bit stride comparison of 2 byte arrays. We're using it for some atomic stuff. We wanted to have lowest possible level. It's a language runtime. I figured that's probably a valid use of unsafe. But we're looking for improvements here. Now, the class hierarchy analysis is one that I really hate because we've got some ugly code sprinkled around to avoid it. So down at the bottom is a call site for object.getMetaClass. It's an interface method coming off of iRuby object. And there is, actually this should be final, there is exactly one implementation of this in our code base. It lives on Ruby basic object, which is the primordial top object of the Ruby object hierarchy. Does anybody know how this optimizes at the JVM level? What's going to happen here if we make this call? And we see 3 different subclasses of Ruby basic object that we want to call getMetaClass on. See, no one knows this. I had to look at the assembly to figure out that it was not optimizing the way I want. This will cross the boundary for a megamorphic call site or polymorphic call site because at the call site, all it sees is Ruby string, Ruby array, Ruby object. It doesn't know that the implementation of this method lives above them. They all share it. All it sees is that the type is different at the call site. So this is a 3 polymorphic call site, and it will not inline getMetaClass anywhere. And this call is made so frequently, so heavily, we have to get the metaclass, the class table data. We had to find a way to fix this problem. And the sad thing is that we have code like this sprinkled all over the code base. And this is a substantial improvement when we're hitting this code very hard. Doing the instance of and cast is way cheaper than letting Hotspot fail to optimize the getMetaClass call. This is the kind of stuff I hate. And this is the kind of stuff that you can't figure out unless you go down to the assembly level and you can see that it's not optimizing the getMetaClass call the way it's supposed to, or at least to the inlining level. So this is the kind of stuff we want to work with the JVM folks and fix. All right, next section. So we've got Ruby running. We want it to be compatible as much as possible, be able to run all the Ruby applications out there, which is, again, very difficult to do. So JRuby's strings, or Ruby's strings we'll start with here. In Ruby, there is one representation of an arbitrary length byte chunk, which is string. Regardless of whether you're doing character data or binary data off the wire, it's string. String object is a byte array. Byte array, it goes in string pretty much universally. It also supports in Ruby 2, or Ruby 1.9 and higher, Arbitrary encodings for all of those byte arrays. So the string aggregates a byte array and an encoding, and that's a representation of whatever data it is. If it's binary, it aggregates a 8-bit ASCII or binary encoding as the encoding for the byte array. Initially, we wanted to just be able to use Java Lang string builder, character arrays, and whatnot to integrate better into the platform. But it was really difficult once we got to dealing with binary data. Every read from an I.O. would end up being either completely bogus character array because we'd pack the bytes into each character, or twice as big as it needed to be because we'd use only the lower byte of each character. So that doesn't work. There were also data integrity issues. If we didn't make damn sure that the JVM didn't try to validate that these were real characters and real code points, we could get binary data that would get Unicode question marks all over it. So we had to make sure we were encoding things and decoding things properly on the way in and the way out. It sucked. So really the first big decision that I helped make when we got to the project was that we were going to go with byte array-based strings. And it's been a challenge, but very rewarding, very, very much the best choice. So that meant a lot of porting. We had to make our own string class that used a byte array and an encoding representation. We couldn't use Java's regular expression engine because we didn't want to decode everything into strings, do the match, and then re-encode back into bytes again. So we had to port a C-based regular expression engine called Oniguruma. We did the encoding subsystem, transcoding other stuff, a little bit more details on each of these. Joni is our regular expression library. It is a port of a C regular expression library called Oniguruma, which has pluggable grammars. So you can choose basically any regular expression grammar you want or write your own. It supports arbitrary encodings. Using this separate encoding subsystem, it pulls characters off of this byte array regardless of what they actually are and does the matching internally, so it can support any encoded text without decoding it. And it has a bytecode, an interruptible bytecode engine in our implementation, so it doesn't deepen the stack. You can very easily blow the JVM stack with trivial regular expressions using Java util regex, which is one of the reasons that we started looking at other regular expression engines. And interruptible, we added the appropriate interrupt checks at key points in the bytecode engine's execution. So if you have too long a running regular expression, you can actually interrupt the thread. It'll bail out and say it couldn't complete the match. Something else you can't do with the Java util regex stuff. This has actually been reforked and made back into a character array-based regular expression engine for Nashorn because the Java util regex stuff was not meeting the needs of a JavaScript implementation, JavaScript regular expression behavior. So hopefully that may eventually even get into OpenJDK to replace the now aged Java util regex code. And there's a repository for it if you want to go look. Did some quick performance numbers last night. If I have a byte array that I got off the wire and I need to do a regular expression match in Java, there's a lot more overhead. You have to deal with the char buffers, you have to deal with decoders for the char set stuff. And then, hopefully you don't have to go back out to bytes after you've done your regular expression logic because you're going to go right back out the other way and do all that same overhead again. In our case, we can go directly from the bytes. They can be encoded in whatever encoding they want to be, but we can do the regular expression match without having to decode everything into character array and then back out to bytes again. So this is a very simple one. Just have a byte array in hand that has A through Z in it and do a modest regular expression match against it. Twice as fast as using Java util regex, mostly because of that character transcoding overhead. If I mix I.O. in here, it gets a little bit closer, but again, even with I.O. overhead in here, there's still a substantial improvement from not having to decode all those bytes into characters. So if you're doing any of this, like raw, low-level, reading off the wire, doing some regular expression matches, doing some other stuff with it, processing that data, Joni might be worth looking at because you're losing a lot of time creating character arrays. So JCodings is the subsystem that handles all the encoding logic, character decoding and encoding to and from bytes. Used heavily by both Joni and JRuby internally when we need to do individual character matches over a byte array that's not necessarily a regular expression. We use JCodings logic to figure out what the next code point in the list is. The transcoding tables and whatnot, may have something more. Nah, I guess I don't have another slide about this. There's also all from any of these encodings to any of the other encodings, it has a mapping of how the characters should map, whether there needs to be an intermediate translation, like need to go to a Unicode format and then to the target format. But again, this is all still working directly against byte arrays. So you can do character transcoding from one encoding to another, do regular expression matches, do any processing along those lines, and never create a character array or a Java string at all. This was the only way that we could make this stuff work. And I don't really think I need a graph here. It's pretty obvious that if you're doing character transcoding, for example, you've got shift gist coming off the wire and you need to send it back out as UTF-8, we can do it way faster than the JDK can at this point, much faster. Okay, so in JRuby 9000, we finished porting all this logic, got the transcoding wired up and got it working properly. We also had to do a port of all the I/O logic because the transcoding in CRuby generally works directly against the I/O buffers. It reads it into a byte buffer in the I/O object, in the I/O subsystem, doesn't need transcoding, it needs into another character buffer, and then what comes out of I/O is the decoded characters, or the characters in whatever the internal VM encoding is supposed to be. So there were a lot of fun C calls to emulate, which I'll get to later. Another area in compatibility that's been difficult for us with JRuby is representing fibers. Fibers in Ruby, they're essentially coroutines, go routines, delimited continuations, depending on what terms you want to use. But end of the day, very hard for us to emulate on the JVM. The best we can do, that's interesting. Yeah, so in Ruby, it's not a concurrency model. They only can run on the thread they were launched from, but it is nice for multiplexing that thread across multiple stacks of execution, multiple contexts. Of course, you can turn this into your own state machine, but it sure is convenient to be able to just use the stack as the state machine and swap it out sometimes. On JRuby, as you'd expect, they are just native threads, which limits how many fibers we can have running at a time. MRI is only limited by the amount of memory because they're just doing stack swapping tricks. For us, it's limited by the number of threads we can create, and people do run into this when they're using fiber-heavy libraries and applications on JRuby. The performance, we managed to get pretty good. Transferring from one fiber to another, with the Java util concurrent stuff, if you pick the right ones, it's very important, pick the right ones, the performance is pretty close to the overhead of doing stack swapping at the C level. Not too bad, we can compete, but the resource load is huge. We can pare down the size of that thread stack, but it's still a whole thread, a whole execution stack, all that stuff that has to go along with it, so much more memory used as a result. And the spin-up time for fibers on JRuby is considerably worse. We do use a thread pool, but that only helps the second fiber or the third fiber. The first one, especially after a long delay, has to spin up a full native thread, and it's very expensive as a result. Other hard decisions we had to make compatibility-wise. Object space is a feature in Ruby to allow you to walk the heap. And in CRuby, where they have a conservative garbage collector and they don't move any objects in memory, this is a trivial operation. They just walk the heap looking for objects, and then they can present them one by one. They also don't have concurrent threads, so they don't need to worry about GC needing to run or someone needing to create other objects during that time. It's just the one that's doing object space walk. This was obviously not something easy for us. We didn't want to turn on JVM debugging features or instrumentation. So the first thing we tried was keeping our own separate map of all these objects. And obviously that was way too much overhead, so it's off by default now. You can turn it on if you want, and we will track it separately in our own structures. Tracing functions basically does callbacks for line numbers, calls from one method to another, class definitions, and so on. This is off by default mostly because we didn't want to constantly be pinging to see if it was a trace function we needed to hit. This is used for really primitive profilers, debuggers at the Ruby level. Sometimes a useful feature, but it's used very rarely, so it's not on by default in JRuby. Full coroutines are in CRuby, not possible for us to do on the JVM, not without destroying the code anyway. And there is a C extension API, but it was really too difficult for us to emulate. And it may be the only thing that's hurt us over time. We've kind of just worked on porting a lot of the libraries that people are used to using. So native integration is the third section I got here. So Ruby's roots. Mats is generally kind of considered a C programmer. He does write Ruby, but he also hacks on the C implementation a lot more. You know, kind of like we end up writing mostly Java, working on JRuby. We don't get to do a lot of Ruby most of the time. So the early versions of Ruby, and you can see this in some of the libraries, were largely just a very thin class shim over the top of POSIX functions. Open a file basically did an open call. Select basically did a select call. And so all of these structures had to behave pretty much like the C equivalents. I spent a lot of time early on in JRuby reading libc code to figure out how they've implemented some of these lower level functions so I could fake it on top of NIO and build my own libc on top of NIO, which is on top of libc. But, you know, you gotta do what you gotta do. Like I say, some of these remain, but we knew we needed a solution. There were things that we just couldn't emulate. We can sort of emulate libc IO operations and whatnot. We can't emulate file system metadata operations that don't exist at the JVM API level. So, first off, looking at JNA, and we started working with JNA, we started making a library called JNA POSIX to map as much of POSIX as we needed. Now it's kind of grown to be as much as the world needs, try to make it a general project. Later on, JNR, the Java native runtime, replaced JNA. Wayne Meissner wrote JNR to be high performance, as low overhead as possible, at least get it down as close to just JNI overhead as we can. I did a talk on this last year, so anybody who hasn't heard of JNR and needs to do native calls, take a look at that talk. So this kind of is a cancer in the C Ruby world, and really kind of a cancer in any of the off-platform languages. Eventually, people always seem to turn to C for performance, unless they've got a really good JIT like V8 or something. But Python has this cancer of so many C extensions. Ruby has this cancer of so many C extensions. And the implementations don't get good fast enough, so people keep turning to C to get the performance. Well, then we try to port this to another platform, and we've got this horrible C extension API on C Ruby that gives off regular pointers, real pointers, gives you macro-based raw access to the internals of objects. I mean, this is almost impossible to emulate. We did try. We got a student through Ruby Summer of Code, sort of a Google Summer of Code thing, to implement this for JRuby. And it sort of worked. We were able to get enough of the API that basic extensions would work, but they were incredibly slow because we had to fake all the pointers on the other side, fake all of the memory accesses, and ultimately it just limited what we could do with JRuby, so we disabled it again. I already covered that stuff. All right, so then once we realized that C extensions were never going to be an option for us, we still needed a way for people to bind C libraries. The two use cases for writing a C extension are, I need C performance or some features from C I can't get otherwise, or I need to wrap some library and expose it to my runtime. For the latter case, FFI came along. The Rubinius guys actually came up with the API originally. It's a DSL for binding C libraries. Easier to just show what it looks like. So this is an example of Ruby FFI, and this is what it was just a Rubinius API. Wayne decided he was going to implement it for JRuby, and then why not? Let's implement it for C Ruby. And then we try to promote that people should use this rather than writing a, for example, get time of day C extension. They can just bind it this way with a little bit of Ruby code. And this all boils down to native. Wayne even wired this up in the Invoke dynamic. The call there to get time of day will be one hop to do the Invoke dynamic dispatch on the Java side, one hop on the native side for a bit of generated assembly code that represents the JNI piece, and then we're there. We've got get time of day. We've written no C code, had to compile nothing. This is the advantage of having an FFI like this on the platform. This I showed last year. This is JNR and all of these sub-projects that we've built on top of it. Using those projects, the things that are native in JRuby today, again, POSIX stuff that we can't do at the Java level, the FFI stuff, standard I/O, actually now in JRuby 9000, we're not using system in, system out, and so on. We create our own NIO channel around that uses all native functions and allows us to do select operations on standard I/O, which you can't do on the JDK normally. And then process launching and control, which I'm really excited about now. I talked about this last year, how process builder and process are really, really bad if you want to control sub-processes, which is kind of sad because that's what you use them for. No channel access is probably the biggest one, and it's even worse than that. What you get out of process is a file stream. So you can't do selection on it. You can't get the actual channel unless you dig down underneath the buffering and other stuff. And then we did that originally, and it broke on a bunch of JVMs because they had different structures for what streams they gave us. So we built a new process API on top of the POSIX spawn function, which is available almost everywhere. We'll have to do something probably a little bit different on Windows, but it's been working great on the Unix side. And it allows us to have code like this, like you would do in C or in CRuby, but you can't do this on the JVM. So we're creating 2 pipes here. We're going to spawn out to the cat executable. We're going to route into our in pipe, route out to our out pipe. Error we're just going to dump to a file. We're going to close the child side of each of those pipes in the parent process once we've done the spawn. So the child now has its side of the pipes. We have our side of the pipes. We can read and write from those, no buffering, direct access to that subprocess. We can do selects operation on there to wait for the process to come back with data. And then we can print it back out and finish the whole process. We can actually just do our own wait PID then at the bottom as well. We get a real process ID out. We can wait for this process to complete. This is actually working way better than what we had before. And we're not touching any of the Java process stuff in this, unfortunately. I wish that we could use that and not have to build our own, but we'll spin this off as a library for everyone else. Last section, and remarkably, this is timing out very well. So little usability things that we've done over the years to make JRuby feel better to Rubyists. The first one I did a lightning talk on last year. I'm going to cover again briefly here. JVM backtraces, for anybody who's not writing in Java code, are really horrendous to look at. I mean, they're practically meaningless, especially in some of the newer JVM languages. And we knew that was never going to fly. We couldn't dump JVM backtrace on Rubyists and expect them to continue using JRuby. They would run screaming the other direction. So initially, we maintained our own Ruby trace. We had our own artificial stack internally. Every line would bump the line number, file name would be updated on entry to a function, and so on. This obviously adds overhead to our execution. Once we started adding the JIT, then we could do some other tricks. We emit the JITted version of the code with a mangled class name, so we can mine out what Ruby function this is, what Ruby file it is, and so on, so that we could produce what looks like a nice Ruby trace element without maintaining our own artificial stack all the time. That was in JRuby 1.5 or 1.6 that we actually made that change. And so after that change, all the compiled, the JITted Ruby code no longer had to do any of the artificial stack stuff and could just go straight through and update, or straight through and use the JVM's own backtrace logic. The ahead of time does a very similar thing. I picked on Scala last year, so I'll pick on Groovy more this year. This is a Groovy backtrace. Again, if you're a Groovy developer, you can't get a better trace than this. This is the backtrace you get. I think there is nothing in this section of the backtrace that was actually written by the user. That's kind of sad. You shouldn't see any of this stuff. You shouldn't see any of this stuff. Now this is what JRuby's trace would look like internally. You'll see that we have a lot of the same metadata logic, interpreter stuff, internal methods. But then you'll see some of these methods that are sort of mangled in a weird way with $Ruby $ in there. That's what we post-process to get a backtrace that looks like this out of that JVM stack. So we are doing mixed mode stack traces on top of the JVM for our mixed mode VM that lives on top of the VM. And then we put some color in as well. There's the mangling. I'm running out here, so I'm going to keep going. Command line. Rubyists are typically command line users, so the command line has to behave like they expect it to. And that TTY that we're using connected up to that command line needs to behave the right way. So in order to do this, we worked for years on improving, optimizing, getting better and better at bash, which I've thankfully wiped out of my memory at this point. But getting these epic bash and bash scripts to be able to simulate all of the command line logic we might do if we had a native executable. It still works pretty well, and that's what most JRubyists end up using. But we did create a native launcher based on NetBeans launcher so that we could do that processing and then spin up in the same memory space the JVM, toss the stuff over to it. Okay. That would be interesting if you cared about the performance difference between bash and writing our own. Console support. I'm not going to cover this too much. J-line has been forked all over the place. It still doesn't work as good as most people want. We're looking at some native level read-line libraries right now. Last section here. I'm going to finish it up even though I'm a bit over. So people using the command line for pretty much all of their Ruby development is really bad for us because they're starting up the JVM and JRuby every single time. And this may be the only reason that JRuby hasn't completely won the Ruby world. We're faster, we're more stable, we've got real concurrent threads, we've got access to all these libraries, you can deploy it anywhere in the world, but it takes 15 seconds to start up on some systems. I mean, it's almost impossible for us to ask people to develop that way. To show this graphically, to give you an idea of how bad it is, -E1 is the absolute simplest thing you could run at the command line with Ruby. Gem-help, Ruby gems is the packaging system, so this is just getting the help output for it, and rake -T inside a Rails app, which rake is the build tool, -T shows all of the targets that we hit. This is where JRuby sits, trying to run these things. And if you're somebody who's sitting there running rake tasks to do your tests every time you make a change, we're killing people with this. This is absolutely destructive to our community. We have tried to find the right flags to use to fix this. Client mode, as many of you know, went away. At least the client flag could do something like this. We have to use the new client flag, which is to turn the tiered compiler to only level 1 to get any sort of startup performance out of the JVM at all. And we actually have released our JRuby launchers with a --dev flag that turns tiered compilation on and switches it to the client compiler, because we can't get client anymore. We turn off our own JIT because of all the verification overhead and so on. I mean, this sucks. So we've looked at things like Nailgun to do out-of-process JVM that is kept going all the time. And there's just an endless set of issues. The TTYs are wrong. People spin up threads and walk away from them because they expect the process to die. People allocate memory and walk away from it because they expect the process to die. So Nailgun doesn't work. Then we started looking at drip, which works like this. Every time you start up a command, it runs that command and then starts up the next instance of the JVM you're probably going to want in a few seconds. So it's already ready to go. We overload this a bit more by making it possible to, let's see, drip init. By making it possible to pre-boot some Ruby code. So in the current directory, if you have a drip main.rb, not only will we have drip start up that extra JVM, but it'll boot Rails for you. Something like this. Load up Rails and continue executing. Sweet, 3 slides. So then with all of these tricks that we have to do, so this is JRuby with no changes. You can see why people don't want to use it. JRuby with the tiered compilation flags and turning off RJIT. Tiered compilation stuff is by far the biggest improvement here. About twice as fast, maybe a bit more. So if you're doing a lot of command line stuff, you might want to set that because the tiered stuff is just not doing what it needs to. This is with just drip plain. All it does is start the JVM. We're seeing that the JVM itself is not the problem here. It's running all of our code, booting JRuby. With our drip init, which at least starts a JRuby instance, doesn't boot any of your application code, gets a little bit better. And then if we actually boot Rails or boot your libraries using drip main, now we're finally getting there. All of this overhead just to get a usable command line for users, and it's too much. It's way too much, and we have to have a better option. And this is actually faster than CRuby here. So, the conclusion, fix these things, or tell me how I can fix these things this week, because that last bullet there is probably the worst one, and we really have to fix that. But that's about it. Hope you all have a fun conference. I'm going to be around today and tomorrow. Sadly, I have to leave Wednesday, but I want to talk to you about all this stuff and figure out how we can make the JVM not have all these problems and make it easier to build these off-platform languages on top of it. Thank you.
Let's use a different color.